In this lecture, we'll discuss what is certainly one of the most important mathematical relations, which is the equivalence relation. So before we do that, I'd just like to recall what a relation is. So a relation on, we have a relation on, well, we can have a relation from one set to another, or a relation on one set, which means from the set to itself. So we're going to focus on that in this video. And that is nothing more than a subset of the product. So it's a collection of ordered pairs. Okay. And so as an example, we could have the set A be, let's see, just have A, B, C, and we could have a relation that maybe looks like this. So let me do the same one from the previous video. So we can have A related to itself, A related to B. Let's have B related to C, and C related to B. So the order is going to matter. And one way to represent this, one of the best ways in my opinion, is with this directed graph. So you have your elements. How did I do it last time? I think I had A, B, C. And A is related to itself, so I'm going to draw an arrow pointing back to A. A is also related to B. B is related to C, and C is related back to B. So that's an example of a relation. Okay, so next we want to discuss what an equivalence relation is. So it's a special kind of relation. So equivalence relation is, it's a relation that is reflexive, symmetric, and transitive. And so you don't have to remember these from the previous video. I'll remind you what they are. But it's a relation that has those three properties. Might have more properties in addition to this, but it definitely has at least these three. Reflexive means so let's call our relation R. Let's say it's on a set S. Reflexive means that for every element of S, so for everything in my set, X is related to itself. So this is already not reflexive. C is not related to itself. Symmetric means, by the way, as I'm writing these properties, you should keep in mind an equivalence relation is designed to capture the notion of equivalence or equality. So that's what these three properties are supposed to do. So so symmetric is for every X and Y in S. I'm following through. So if X is related to Y, then Y needs to be related back to S. Back to X, sorry. And then transitive means for every three things in my set, say X, Y, Z, if X is related to Y and Y is related to Z, then the conclusion is X is related to Z. So it's directly related to Z. You can actually verify this one up here as none of these three things. So you should try to do that yourself. But to be an equivalence relation, we need all three of these things. And again, these three things are basically designed to sort of best capture the essence of what it means to be equal. And so let's see if we can do an example now. So here's an example. Let me do an example with the set A. So I'll keep that same set, just A, B, C. Here's an example of an equivalence relation. There are several, but here's one of them. I can just have A related to itself, B related to itself, C related to itself, and no other relations. So what would that look like? Well, I just have A, I have B, and I have C. And this is just my set A. And same up here. In this case, A is related to itself, B is related to itself, and C is related to itself. So this is reflexive. Everything is related to itself. It is symmetric. That might be confusing at first, but let's look carefully at the definition of symmetric. For every two things in S, and they might be the same thing, that's fine too, but for every pair of elements in my set, I need if X is related to Y, then Y has to be related to X. So for example, for A and B, if A is related to B, then B has to be related to A, but A is not related to B. So we have if P and then Q. Remember our conditional, our implication here. So if P is false, then this is true by default. Right, the value is true by default. This is only false when P is true, but Q is false. So saying for every arrow, there needs to be an arrow going back. Okay, and that is true for these. So for example, for that arrow, the arrow going back is just itself. So it needs to be symmetric. It is transitive, sort of for the same reason. Okay, that's a good example. Here's an example of something that's not an equivalence relation, so non-example. We could have the same set, A, B, C, and my relation is just no relations whatsoever. So it's just A, B, and C with no arrows going anywhere. And the problem there is it's not reflexive. Okay, so reflexive is a little different than these two. It actually demands, it's not an if-then, it actually demands for every element of my set, there has to be an arrow going back to itself. Okay. So this is non-equivalence relation. However, this is, and again, this is weird to think about, but it makes sense once you think through the implication. This is symmetric and it is transitive, but it's not reflexive. Okay. Okay, let's look at some examples we're more familiar with, maybe. So here's the big example, just the equal sign. The equal sign relation on any set of numbers we want. Let's say the integers. Okay, and here's what that graph looks like, the directed graph or digraph. I have all my integers, and 0 is equal to itself, but it's not equal to 1, so I don't have any arrows going from 0 to anything else. But I do have arrows on everything going to themselves. So the actual set, like the relation, what is a subset of my product, it would look like this. -2 is related to itself, -1 is related to itself. So this is really what the equal sign is, if you look behind the scenes. It's this relation. Okay. Okay, and that's reflexive, symmetric, and transitive. It's very similar to this one up here. We could have other things that kind of behave like equals but aren't exactly equals. But first, I just want to tell you a non-example would be the less than or equal to relation. It's not an equivalence relation. And it's because it is, it turns out it is reflexive and it is transitive, but it's not symmetric. Not symmetric. And that's because you have examples like 2 is less than or equal to 4, but 4 is not less than or equal to 2. So that prevents it from being an equivalence relation. There's an arrow from 2 to 4, but not from 4 back to 2. You could have various other examples like similarity of triangles is a good one. So similarity of triangles. This is one you've probably seen before, where you have things like, triangle ABC is similar to triangle DEF, meaning they have the same corresponding angles. They might be different sizes and different orientations, etc. But their angles match. And that is an equivalence relation. You can verify that it has these three properties. And in fact, we will take inspiration from this example. So we'll use this symbol. So in fact, we'll use this symbol to indicate, not all the time, but we'll often use this symbol to indicate specifically an equivalence relation. Which is nice, because now I don't have to draw that R anymore. I can just say X tilde Y. But typically reserve that symbol tilde for an equivalence relation. Okay. Another one of my favorite examples is just our set can be the words in the English language. And there are many equivalence relations that you can have. So for example, or let's use a new symbol, this tilde could be, so we can say X tilde Y if X rhymes with Y. If X rhymes with Y. And that's an equivalence relation. Or a word rhymes with itself. If a word rhymes with a different word, then that second word rhymes with the first word. If two different words rhyme with the same word, then those two words themselves rhyme. Okay, but here's a non-example, actually. A non-example would be words that, you have to be a little careful, that share a letter. Okay. If I said the first letter, actually, I think that would be an equivalence relation, but it's words that share a letter. Well, I could have something like cat, and that shares a letter with a cow. It shares a letter with dog. So this part of the graph, I would have actually arrows. I'm sure a cat shares a letter with itself. Right. So I have a lot of relations here, or a lot of connections here. But yeah, it's not an equivalence relation because cat is not related with dog, right? They can both share a letter with cow, but they might not share a letter with each other. So it violates actually this transitive property. So this is not transitive. Not transitive. Okay. Let's just look at some more examples. So here's an example. Let's say let's consider the set of integers, and x tilde y will mean, so where x tilde y means x squared is equal to y squared. It's actual equal sign. And that is an equivalence relation. It's different than this one, because actually in this equivalence relation, you have more things than just a number related to itself. In fact, if I wrote out my relation, it might look like this. So I have 0 is related to itself. 1 is related to itself, but it's also related to -1, because their squares are equal. And similarly, the -1 is related to 1. That could be x, that could be y. I do really need to have them all in here. I can have 2 related to itself. 2 related to -2, you get the idea. And so the digraph here would be, so 0 would be related to itself, and then -1 and 1 are related, -2 and 2 are related, so connections would look like this. These are, of course, related to themselves, but also related to each other, like this. So some more interesting graph here. And one thing to notice, actually, is this relation essentially partitions the integers into different classes. We call these equivalence classes. So 0 is an equivalence class by itself. 1 and -1 are in the same equivalence class. etc. See, so there's one equivalence class, here's another equivalence class, here's another equivalence class, etc. And then we see that in this example too. So every number here is in its own equivalence class. Yes, so equivalence class, yeah, let's define that. So, yeah, definition, an equivalence class, how do I want to say this? Well, let's take a set, let's take an element in a set, and then we'll let tilde be a relation, be an equivalence relation. On A, then the equivalence class of A, of an element, denoted, there are lots of ways to denote it. This is probably the most common. You have these brackets. And what is it? It's just a set of all things related to A. So it is a set, so it's all the B and A such that, is my set builder notation, such that B is related to A, or A is related to B. It doesn't matter which way I put it because it's an equivalence relation, it's symmetric. So that is an equivalence class. So here, this is an equivalence class. All things related to -1 are itself and 1, right? And so that's the idea. So an equivalence relation will always sort of partition your set into equivalence classes. For example, the words in the English language also that rhyme, that would be, so cat would be in a class with every single word that rhymes with it. Okay, let me show you a very important example now. I think we're ready for this one. This is one you might have seen before. So define a relation tilde on Z. This is how I should have phrased this up here too. Suppose I think the best way to phrase something too late. Define a relation tilde on Z by X is related to Y if X minus Y is, let's say, a multiple of 3. There's nothing special about a number 3. I could have replaced it with anything, but 3 is an interesting case. So what does that? What do I mean? So i.e., what does a multiple of 3 mean? It means this is 3k for some k an integer. All right, what does this look like? So it's a relation on Z, so but it's different than these two. It's very different, in fact. So for example, let's start with the number 2. Well, 2 is, what's 2 related to? 2 is related to 5, actually. It's 5 minus 2 is a multiple of 3, so 5's in here with 2. And so is 8. 1 is not in here, though, right? Because 2 minus 1 is not a multiple of 3. And sure, there's -1 in here also. And -4. Right? 2 minus -1 is 3. That's a multiple of 3. There's 11. There's all kinds of numbers in here, right? And technically, you have arrows going everywhere, right? But I'm going to stop drawing the arrows. That's another good thing about equivalence classes. When you have an equivalence class, let's have a big equivalence class here. So everything in it has arrows to everything else. So that's one equivalence class. And there's some things that are not in here, like 1. And 1 is in here with negative, well, it's 4 and -2. And 7 and 10. Right? 10 minus 1 is 9. That's multiple of 3. And many other numbers. So this is a different equivalence class. And I, in fact, have a third one, which has just the multiples of 3. Is it different how many multiples of 3 is a multiple of 3? Those are all in their own class. They're not in one of these classes, it turns out. And so I have, it turns out I get exactly 3 equivalence classes. So this one we could call it, bracket 2, I could call it bracket -4, bracket 11, it doesn't matter. This is one way to indicate this whole equivalence class. Everything related to 2. Here's everything related to 1, everything related to 3, or let's say 0 even. And a name for this. So there's a special name for this. So the name for this particular tilde, this particular relation, is congruence modulo 3. You might have seen this before. So when you've done modular arithmetic, you're really working with equivalence classes under this specific equivalence relation. So there's kind of a smudge there. I want this to be very clear. So it's saying if x minus y has to be minus. I think if you put a plus, it actually doesn't give you an equivalence relation. But yeah, if x minus y is a multiple of 3, this turns out to be an equivalence relation. And we're going to prove that, actually. But yeah, this is called congruence modulo 3. It's also denoted this way. X is congruent to y, triple equal sign. And then you put in parentheses modulo 3. That means x minus y is a multiple of 3. And this is an equivalence relation. It's actually a very important equivalence relation. So let's actually prove it's an equivalence relation. Let's prove it. So this will be our proposition. How should I say it? Congruence modulo 3. Is an equivalence relation. That's not something that comes for free. That's something that we have to prove. Because again, I said if you change this slightly, like if you have x plus y, it's not going to work anymore. It's not even an equivalence relation. I think you lose transitivity probably. Here we go. Congruence modulo 3 is an equivalence relation. What is the proof of that? So here's how we prove it. We have to check all these 3 things. So let's go ahead and do it. The first thing is it reflexive? So let me just write down here exactly what we mean by let's call it tilde. And again, we say, so recall x tilde y means, it's a definition that's good to memorize. It means that x minus y is a multiple of 3. It's 3k for some k and z. Okay. So here's the proof. We need to check it's reflexive. Why is it reflexive? So let's think through the thought process. So I want to show, is x congruent to itself? Modulo 3 is a number congruent to itself. So let's go back here. I need to show that for every x, for every integer x, it's congruent to itself. I'll let x be in z. Is it congruent to itself? Well, yes, because how do we show that? We have to use a definition, right? So because x minus x is, well, what is x minus x? That's obviously 0, but 0 is a multiple of 3, right? So that checks out. That checks out, right? is it symmetric? So how do I want to start? Let's remind ourselves what symmetric means. It's for every two integers, every pair of two integers, if one is congruent to the other, then the second one is congruent to the first one. So let's check that. So we'll start by letting x and y be arbitrary integers. And we want to assume, again, we're proving a conditional. We're trying to prove this conditional. So to prove a conditional statement, to prove an implication, you assume this part is true. So I want to assume x minus y. So x is related to y, i.e. x minus y is a multiple of 3. So it's 3k for some k and z. Okay. Then I want to show y is congruent to x. That would mean y minus x is a multiple of 3k, or is a multiple of 3. And it's not exactly the same as x minus y. However, I can pull out a negative sign. And I do get exactly x minus y. So that's negative 3k for that same k, which is a multiple of 3. It's 3 times negative k. Right? So y is congruent to x. That's what we proved. Perfect. The next part, is it transitive? Where do we start with this one? So, see if you can do it without even looking back at the definition. So we need 3 things. We need x, y, and z in the integers. And what are we going to assume? Well, we're going to assume x is related to y. So in other words, so x is related to y, and y is related to z. So in other words, what does that mean? It means x minus y equals 3k for some k and z. And y minus z is, I don't want to say 3k, it might be a different multiple of 3. So I'll say 3l for some l and z. Right? What do I want to show? Then I want to show x minus z. I want to show x related to z. So I want to show x minus z is a multiple of 3k. And this one's actually a bit fun, so it's not super obvious. Why is x minus z a multiple of 3k? If x minus, or a multiple of 3, sorry. Well, I need to use these somehow. Right? I need to use these facts somehow. And so I'm going to try to make these appear. I'm going to rewrite x minus z as x. Is this going to work? X minus y plus y, that's just plus 0, minus z. And now I see both of these things, right? X minus y and y minus z. And so x minus y is 3k. You might have also gotten an inspiration by noticing that if I add these two equations, I get x minus z. So we get x minus y is 3k, y minus z is 3l. So overall, this is 3 times k plus l, which is a multiple of 3, right? So x is related to z. So this is an equivalence relation. It's reflexive, symmetric, and transitive. Okay. All right, so I'd actually like to conclude this video with 2 important facts that will apply to any equivalence relation. And these are going to be evident in all the examples we've done. And so the first one is an equivalence relation. It's one I already mentioned, but I want to go into a little bit more detail. So an equivalence relation partitions a set. Partitions a set. But I mean, so into distinct components, distinct subsets. And so, yeah, partition of a set is basically you're writing your set as a union over distinct subsets, each of which has to contain at least one thing. And so we've seen this in the examples. Like this is a partition, this is a partition, this is a partition. It only has three things, but this is a perfectly fine partition of the integers. Every integer is in one of these three, and they're all distinct. So why is this true? Well, the idea is given two elements in your set. So given x and y in your set, let's call a set of something. Either their equivalence classes are the same. So equivalence classes are exactly the same. They have all the same elements, or they are totally disjoint. And this is a good example to keep in mind. The integers modulo 3. So x and y are totally disjoint. And one way to write that, kind of a clever way to write that, is their intersection is nothing, is the empty set. So it's saying they're totally disjoint. And well, why is this? So either they're the same. So like if x and y are themselves equivalent, well then they'll be in the same class, right? So we have a picture like this: x and y are equivalent. But then if I have something over here that's equivalent to x, right? Well, transitivity dictates it must be equivalent to y too. So I just get anything that's equivalent to x is also going to be equivalent to y, and vice versa. Anything equivalent to y is going to be equivalent to x, and essentially because of transitivity, which comes with the equivalence relation. And why are they completely distinct if they're not equivalent? Well, suppose I have x and y, and okay, they're both in some equivalence classes, but let's suppose they weren't distinct. Let's suppose, for the sake of contradiction, they overlapped here at some element. Well, again, yeah, that would force y and that would force x and y to be related, again, because of this transitivity, which is a contradiction because we're assuming that they were not equivalent. So that's the idea. That's why you get these this partition. And then the second fact, well, it's just this one, it's the converse of this essentially. So given a partition of a set, so conversely, let's say there's no equivalence relation in the picture. Oh, and by the way, I should say that any element has to belong to one of these sets in the partition because it's equivalent to itself, right, by the reflexivity. But conversely, a partition of a set, actually, let's say there's no equivalence relation in the picture, well, we can bring one into the picture that'll give you precisely that partition. So it essentially defines an equivalence relation. And I'll show you how you might do this in a picture. So relation. So let's say I have some set, and it has some elements. So let's say I've got an element A. Let's say I want to partition A off and do its own subset. Let's say I have B and C. Maybe I want to partition those off. And maybe I have some more elements down here. And how do you define the equivalence relation? Well, you essentially just say everything in each subset is equivalent to everything else in that subset. So A is equivalent to itself. If we don't say that, then we don't get an equivalence relation because it's not reflexive. So you need to say everything is equivalent to itself by default, and then everything is equivalent to everything else in its partition. So you can actually partition a set however you want, and then you can use that to define an equivalence relation. And so you define the equivalence relation tilde by x is equivalent to y if here, let's call this like S1, S2, S3, etc. If x and y belong to the same subset of the partition. Do the same subset in the partition. Okay, so If I start with an equivalence relation on a set, I get a partition. If I start with a partition and no equivalence relation, I can build an equivalence relation. And again, the way you do that is you say this. You say, everything in the same subset is equivalent to each other. I don't want to draw in all the arrows, but you have to draw in all of them. Here, I don't want you to get the wrong idea, so I'll try to draw out everything. But yeah, you get the idea. Technically, you would have to now prove that this is reflexive, symmetric, and transitive, but that follows fairly easily, as long as you draw in all the arrows. So reflexive, symmetric, and transitive all follow from this construction. Because again, you're drawing in all the arrows. You're saying something is equivalent to anything else in its subset. Okay. All right. So just as a final note, so think back to our modular arithmetic example. So as a result, we can think of the integers mod 3 as the integers under this equivalence relation, tilde, which is we define two integers to be equivalent if their difference is a multiple of 3. So we can think of this, the integers mod 3, as just having, well, what happens, we get a partition into 3 subsets. It partitions the integers into 3 subsets. So the way to think about this is they're just 3 numbers. Just having 3 numbers, but I'll put numbers in quotes because it's kind of like one super number that includes the entire subset. But they're completely distinct and they cover everything. So my 3 numbers are the congruence class, the equivalence classes, also called congruence classes in this case. Okay. And we'll explore this idea of modular arithmetic a little bit more later. Yeah, that's it on equivalence relations. So hopefully you found this useful, and I'll see you in the next one.